Hello and welcome to this video. So this is a video for CE 105 on the properties and structure of glasses. And so in the previous lecture, we have seen the definition of what is a glass, the typical application of glasses, and the how to make a glass. And so now what we are going to talk about in this video and in the following one is what is the what is the atomic structure of glasses. And the structure of glasses, the way the atoms are arranged with each other within a glass, that's something that's important because this is really what is going to govern the properties of a given glass. And if you change the structure, the atomic structure of a glass, then its property is also going to change. So when in the process of designing new glasses, when you design a new glass and you want to come up with a new glass formulation that has certain properties, then usually you will need to change its structure in order to achieve the property that you want to achieve. So in this video, we are going to see how to characterize the structure of glasses. And characterizing the structure of a glass is very different from characterizing the structure of a crystal. And the tool that we are going to use to characterize the structure of a glass is the pair distribution function. So we are going to see what is the pair distribution function and how we can interpret, how to calculate it and how to interpret it. So the main reason we need this tool for glasses and that we don't need it for crystal is that the structure of a crystal is very different from the structure of a glass. If you take a crystal, then by definition of a crystal, the structure of the atoms within the crystal is going to be periodic. It means that in a crystal, the atoms will form a lattice, so the atoms are periodically distributed. And so in that kind of situation, so if you have, like, for example, like two types of atoms like this, atom A and atom B, they will form a lattice. So they will be periodically repeated in the space. And in that case, when you have a crystal like this, the way to characterize the structure of a crystal is not to give the position of each atom XYZ, because that would be redundant information because we know that the structure is periodic. The minimum amount of information that you need to provide to describe the structure of a glass is simply to define its unit cell, to identify what is the minimum volume that can represent fully the structure of the crystal by being periodically repeated. So in this case here, if you defined this square here, so this is the unit cell of the crystal, it means that if you repeat periodically this unit cell, then you will describe the entire structure of the crystal. So in that case, all you need to do to fully describe the structure of the crystal is to describe its unit cell, to say that you have one atom here and one atom here, for example. And then once you repeat this unit cell, then you will form the entire crystal. For example, like here, now you will have this atom here and this atom here. If you put it on the right, you have this atom here and this atom here. If you put it on the left, then it's the same thing. So you can form the entire structure of the crystal by periodically repeating this unit cell. So in that case, all you need to know is this information. You need to know what is the unit cell, what is the size of the unit cell. Is it a square lattice, or is it another kind of a lattice? And where are the atoms within the unit cell? That's the only thing, that's the very minimum amount of information that you need to provide to fully describe the structure of the crystal. In a glass, you cannot do that, because in a glass, the atoms are randomly distributed, or maybe not randomly, but at least you have no periodicity in a glass. So if you look at the structure of a glass, that's going to look like something like this. You cannot define a unit cell that would be periodically repeated. That's by definition of a glass. A glass is non-crystalline, so there is no unit cell that you can define. And in that case, if you really wanted to describe the structure of the glass, you would need to provide the position of all the atoms. You would need to look at atom by atom, what is its position XYZ within the space. So that would be something that if you have like 10 to the power 23 atoms, then for each of those atoms, 10 to the power 23 times, you would need to provide its position. So that's something that is obviously impossible. That's too many degrees of freedom. That would take a very large amount of information to characterize all the position of all the atoms within the glass. So since we cannot know where the atoms are due to this absence of periodicity, rather than providing exactly where the atoms are, what we do for glasses is that we rely on probability. Rather than saying atom 1 is here, atom 2 is here, atom 3 is here, we are going to rely on probability. We are going to say that there is a given change that this atom is at this position and another probability that another atom is at this position. So rather than relying on an absolute description of the structure of a crystal, this you can do it for a crystal, you can absolutely say where the atoms are. We are going to rely on a probabilistic description for the structure of glasses. All we will rely is to define some probability. And the reason that we rely on probability rather than absolute information is because for glasses, we cannot, that would take too much information to provide the detail of all of the position of all the atoms. So it's much more convenient in the case of glasses, but also in the case of liquids. Every time you have a structure that is not periodic, then it's much more convenient to rely on a probabilistic viewpoint, to rely on probabilities to describe the structure of the glass. So to illustrate what is this pair distribution function, which is the function that we are going to use to describe the probability of finding atoms at certain position, let's consider an example. So assume that you have a glass that contains n atoms within a volume V. So that would be something where you have some atoms like this. So you have those n atoms within a given volume V. So you have a volume V, which can be a cube or something else, and you place those n atoms within this volume V. So the first thing that is an important property to describe in this case is to first look at what is the average density, what is the particle density of the atoms within the glass. And so for this, if you look at this average density, the average density is going to be the average number of atoms per unit of space. So it means that if you look at a given volume dV, so you define a small infinitesimal volume within the glass, so the density within this volume. So first, if you look at the density within this volume, how to get the density? You need to count the number of atoms inside this cube, and then to divide this number of atoms by the volume. So here I'm using some D notation because it's a very small cube, so you will find a very small number of atoms within a very small volume. And so this defines the density. The density is the number of atoms per unit of volume. So now, if the atoms were perfectly homogeneously distributed, so perfectly randomly distributed throughout the volume, then you would expect that the density is just going to be equal to the average density. Like, what is the average chance to find some atoms within this volume? The average number of atoms that you will find within this volume is just going to be equal to the total number of atoms divided by the total volume of the box. If you look at the total number of atoms that you have in your glass, and you divide by its volume, and so if the atoms are randomly distributed within the volume, then your average chance, your average number of atoms that you will find per unit of volume is going to be equal to the average density, the total number of atoms divided by the total volume. So this is only assuming that the atoms are purely randomly distributed within the box. If the atoms are not randomly distributed, then it's possible that within this box, in certain region of this box, maybe you have a lower chance to find some atoms that and some other region within this box, you have a higher chance to find some atoms. If there is some kind of heterogeny, if some parts of this box have a higher chance to contain some atoms than others, then the density at each point will not necessarily be equal to the average density. You might have some points that will have a higher density, some points that have a lower density. So here, the idea of the pair distribution function is to look at what is the deviation from this average density. At a given position, is there going to be an excess of atoms with respect to what you would expect from the average density, or is there going to be a deficit of atoms? So that's the idea of the pair distribution function. It's going to look at a given point, do you have will you find just the average density? It means that if at a given point the density of atoms is equal to the average density, then it means that at this point the atoms are just randomly distributed. But if you find that at a given point the average density that you find, or the density that you find, is lower than the average density, then it means that there is going to be a deficit of atom at this point. You have a lower chance to find some atoms at this point from what you would expect if the atoms were randomly distributed. And on the other hand, if the density is higher than the average density, then you have an excess of atoms. So those are the three cases. So if the density is higher than the average density, then you have an excess of atom at this point. If the density is lower than the average density, then you have a deficit of atoms. And if the density is just equal to the average density, then it means that you have no excess, you have no deficit, you have exactly the number of atoms that you would expect if the atoms were just randomly distributed with no specific preference from a region over another. So this is really what the pair distribution function will capture. The pair distribution function will capture how much the density at a given point deviate from the average density. Do you have an excess or do you have a deficit of atoms? So now what matters is not the density at a given point, right? Because if you just take the glass and you just translate this piece of glass, then all the atoms of this glass are going to move together to a new position. So the position at which the atoms are does not really matter. What matters is their position with respect to each other. If you take a piece of glass where the atoms are just frozen, the position of the atoms are frozen, if you move this piece of glass, all the position of all the atoms will change, but what will not change is the position of the atoms with respect to each other. The distance of the atoms with respect to each other will not change. So what really matters is not the position of the atoms. What matters is their position with respect to each other. So what we will do to do this is that we will look at what is not just the density of atoms at a given position, but we will look at this with respect to other atoms. We will look at a certain distance from one atom, what is the density of atoms at this distance with respect to another atom. So the way we will do that is first we will define a reference atom, a central atom. So this black atom here is going to be your reference. So there is no specific reason to choose this atom over another one. So what we will do is every atom eventually is going to be the reference. But just for the sake of the illustration, we will look at first at this atom. And then what we will define is at a given distance r from this reference atom, what is the local density of atom? And so we will define this. So we will define rho at the distance r. This is the local density of atoms at a distance r from the central atom. So this is the distance r from the central atom. So again, the central atom does not matter. You can select any atoms for this, or you can just select all the atoms one by one within the glass and define for all the atoms what is, if you look at a distance r from this central atom. So you can define a sphere here. The sphere will define all the atoms that are at a different distance r from the central atom. You look at this distance from the central atom, what is the local density of atoms. So this is going to be a local density here, because this is only the density at a certain position. It's not the average density within the box. It's really the density at this distance r from the atoms. Okay, so now let's see what we can do with that. So we can calculate the density of atoms at this distance, and the way we'll do that again is to look at how many atoms do you have at this in a small cube around this position, and you divide by the volume. So you define a small infinitesimal volume at this distance. You count how many atoms do you have, and then that gives you the local density of atoms at this distance. And so what really matters here is, if you look at the local density of atoms at this distance r from the central atom, is it going to be higher than the average density? Then in that case, it means that at this distance you have an excess of atoms. Or is it going to be lower than the average density? And in that case, it means that you would have a deficit of atom at this distance. So what really we want to check here is that if you have this central atom here, you want to look at, if you look at certain distance around this atom, so if you take different distance r, will you have at those distance a high chance to find an atom or a low chance to find an atom? And this is what we are going to capture by the pair distribution function. And so what we are going to use as a definition of the pair distribution function is as follows. What we want to capture with this pair distribution function, which is typically abbreviated as a PDF, we are going to define this as the ratio between the local density at a given distance with respect to the average density. So we are going to define the pair distribution function. We are going to write it g of r. And so we are going to write it like this. We are going to say that the density of atoms at a given distance r is equal to the pair distribution function times the average density. Another way to write this is that we define the pair distribution function g of r as the ratio of the local density of atoms at this distance r divided by the average density. So if we go back to what this means, it means that if you look at this, so if you have an excess of atoms at a given distance, for example, if there is one distance here around the central atom where you find a lot of atoms, so there is one certain distance around the central atom where you find an excess of atoms, then in that case it means that at this distance the local density at this distance is going to be higher than the average density. You have a high chance to find some atoms. In that case, it means that by definition, since you have a high chance to find some atoms, the local density will be higher than the average density. And if the local density is higher than the average density, it means that g of r is going to be larger than 1. This is what you expect when you have an excess of atom at this distance. But now, if you look at certain other distance, like for example, this distance here that is very close to the central atom, if you're very close to the central atom, you have a very low chance to find another atom, because if they were so close to each other, they would start overlapping. So you have certain distance where you have a very low chance to find another atom. And in that case, it means that if you have a low chance, if you have a deficit of atom at this distance, then the pair distribution function is going to capture the fact that at this distance, the local density of atoms is lower than the average density. And if the local density of atom is lower than the average density, then it means that the pair distribution function will be lower than 1. So pair distribution function lower than 1 at a given position means that there is a deficit of atoms. And finally, so if you were in a case where you are at a distance where the density of atoms is going to be equal to the average density, then in that case, the pair distribution function would be equal to 1. In that case, this means that at this distance, you just have a random chance to find some atoms. There is no deficit of atoms, there is no excess of atoms. Your chance to find some atoms is just given by the average density within the glass. So this is what we will use to describe the structure of a glass. We will calculate at different position. We will calculate the value of the pair distribution function at different position. We will look at if you start from a central atom, if you look at certain distance, certain increasing distance, if you look at all distance around this central atom, what is your chance to find some other atoms? Do you have a high chance? In that case, pair distribution function will be larger than 1. Will you have a low chance? In that case, pair distribution function will be lower than 1. Or will you have a random chance? In that case, the pair distribution function would be just equal to 1. So if you plot the pair distribution function as a function of r, that gives you the probability to find some other atoms at certain distance. So this is the tool that we will use to describe from a probabilistic viewpoint what is the chance to find some atoms at each distance. So now let's see some typical example of pair distribution function. And for this, let's start with, for example, what would be the pair distribution function of a crystal. So in a crystal, the atoms are periodically distributed within a certain lattice. So for example, let's take an example like this with a square lattice. And so in this case, if we want to draw the pair distribution function for this, so what we will do is that we select one atom, one central atom, but the result does not depend on which atom we select. And then we start looking. So we start looking at, for different distance around this central atom, what is your probability to find some other atoms? So what we do for this is that we are going to start looking at, for a certain distance r, what is your chance to find some atoms? And then we start to grow. We calculate this at a certain distance r by gradually increasing r. And then we plot the pair distribution function g of r. So as a reminder, the pair distribution function is going to be the ratio of the pair distribution function is going to be the ratio of the local density of atoms at this distance r divided by the average density of atoms. So if you start by taking some small distance r, then initially you will never find another atom. So it means that your local density around the central atom initially is going to be 0, because you have a 0 chance to find another atom at this distance. You cannot have two atoms that are at the same position, then they would overlap with each other. So initially, your pair distribution function will be 0 in a crystal. Then if you continue increasing the distance, at some point here, there is a very specific distance that corresponds to the distance at which you find the first neighbors. So if you look at this distance here, so if you take a sphere with this radius here, at this distance r1 here, you find 4 atoms. So this means that at this distance, you have a very high chance. You have a very strong excess of atoms. So it means that at this distance r1, suddenly the pair distribution function will become very high, because suddenly you have a very high chance to find some atoms. Now if you increase that a little bit, again, you have a very low chance to find some atoms. There is no more atom at this distance. So again, the pair distribution function will go back to 0 at this point, something very close to 0, because you have a very low chance. So next, the second distance where you find some atoms is going to be this distance here. This distance corresponds to the second neighbors of atoms. So this is where, again, you have a very high chance to find some atoms. So this is going to be the distance r2. Now you have found the second neighbors. So again, at this distance, you will find a very high peak of atoms. Again, if you increase a little bit more, again, you find a very low number of atoms. So it means that your pair distribution function will decrease again. So again, it will go back to a very low value, etc. So then if you increase again, now you will find those atoms here. So you will find the third neighbors. So those atoms here. So again, you will have a peak. So at this distance here, which would be R3, then again you find some atoms, etc. So if you continue increasing the distance, then what you will get is something like this with certain peaks that you find. So this is what you would get for a crystal. For a crystal, you will find some clearly defined peaks that corresponds to the first, the second, the third neighbors, etc. And every time you find some neighbors, every time you find one distance that corresponds to the distance between the central atom and the first, second, and third neighbor, etc., then that will correspond to a very sharp peak in the pair distribution function. So now let's see a second example of pair distribution function, and now we're going to take virtually the opposite, which would be a perfect gas. So by definition of a perfect gas is a system where the atoms do not see each other. In a perfect gas, the atoms are randomly distributed within the space. The atoms are moving within a given volume, and they do not interact with each other. That's by definition of a perfect gas. They do not interact with each other unless they are exactly at the same position, and then they would just collide with each other. So in a perfect gas, the atoms do not see each other unless they bounce on each other. So in a perfect gas, if you look at what would be the position of the atoms within a perfect gas, it's purely random. Like, the atoms do not see each other. So if the atoms do not see each other, then there is nothing that would push the atom far away from each other. There is nothing that prevents the atom from being close to each other. So in a perfect gas, the atoms are perfectly randomly distributed through space. So now if we look at what would be the pair distribution function of the atoms within a perfect gas, then again what matters is that you have to look at what is the density of neighbor at a given distance from the central atom. Compare this to the average density, and this gives you the pair distribution function. But in a perfect gas, the atoms do not see each other. So there is absolutely no reason that there would be certain distance with a deficit of atoms or certain region with an excess of atoms. In a perfect gas, there is nothing that pushes the atom away from each other. So there's nothing that prevents the atom from coming close to each other. So there's nothing that there's no reason that certain distance would be more populated than others. So if you look at in a perfect gas, you take a given distance r and you look at what is the average number of atoms that I will find at this distance. In a perfect gas, the average number that you will find at this distance is going to be exactly given by the average density. In a perfect gas, the atoms do not interact with each other. So they are not going to create any region with a deficit or any region with an excess of atoms. So in a perfect gas, what you would find is that the pair distribution function is always equal to 1. It's because in a perfect gas, the local density is always equal to the average density. There is no excess and no deficit of atoms. So if there is no excess, no deficit, the average density is always equal to the local density. In that case, the pair distribution function is equal to 1. So when you have a pair distribution function like this equal to 1, then it means that the atoms are just randomly positioned, just like in a perfect gas. There is no excess, no deficit. So finally, let's look at what would the pair distribution function look typically in a glass. So if you look at the structure of a glass, in the structure of a glass, the atoms are not periodic. So there is not going to be some clearly defined peaks like in a crystal. But on the other hand, if you look at the structure of a glass, it's not perfectly random either. It's not like a perfect gas. So a glass would have a structure that is somewhere in between that of the crystal and that of a perfect gas. So if you look at what would be the structure of a glass, typically it's something that would look like this, where the atoms are fairly randomly distributed, but not perfectly randomly either, because in a glass, the atoms will still interact with each other. So for example, the atoms will not come very close to each other. There will be some repulsion in between the atoms. So if we look at the typical structure of a glass, so let's take the central atom. So for example, let's take this one, and let's see what the pair distribution function would look like in this case. So again, what we are going to do is look at what is, for a given distance r from this central atom, what is the local density. We are going to then compare this to the average density, where the average density is just the total number of atoms divided by the total volume, and that is going to define the pair distribution function. So let's plot this pair distribution function, g of r, as a function of the distance for the case of a glass. So let's see what it looks. So again, let's start. So let's increase the distance. Initially, if you look at a glass, initially at very small distance, it might look actually not that different from a crystal, because again, if you look at very small distance r, initially you will not find many atoms, because you cannot have two atoms at the same position. So again, you will have a range of distances here where you will find no other atoms. No other atoms means that the local density would be 0. In that case, the pair distribution function also would be 0. Then again, now you will start to see some distances here. So there's a range of distances here where you have a pretty high chance to find some atoms. Now the difference between the crystal and the glass is that in the crystal, the atoms are forming a perfect lattice where the atoms are perfectly at a perfect distance from each other. Now in a glass, certain atoms are at a certain distance from each other, but like this distance is a little bit variable because the atoms are not perfectly at the same distance from each other. So it means that now, rather than having a very sharp peak where all the atoms, you would always find them at the same position, in a glass, what you will get is some kind of broad peak like this, because you have a range of distances over which you have certain probability to find some neighbors. So then if you continue increasing the distance, again, maybe there is a range of distances where you have a very low chance to find some atoms. It's because now you have found those 4 neighbors here, for example, and those neighbors themselves, they will have a low chance to have some other atoms exactly at the same distance. So usually after you have found the first neighbors, so this is the first neighbor, or we call this the first coordination shell. The first coordination shell is the shell that contains the first neighbors. Usually after that, you have a very low chance to find some other atoms very close to the first coordination cell. So again, the pair distribution function will go back to something very close to 0. Then if you continue, then you will start finding again now the second neighbors. You will start finding some a region where you have again a pretty high chance to find some neighbors. So that's going to give you a second peak. This peak is typically going to be broader than the first peak because now you go at a higher distance, so you start to have even more disorder accumulating. So the range of distance where you will find those atoms will have even more variability. So you will start to find a broader peak. So this is going to be now the second coordination shell. That's going to be the shell that contains the second neighbors of the central atoms. And then after that, if you continue increasing the distance, now you will start finding the third neighbors. So you will start to find a region that contains the third neighbors. So you will find again another peak that contains now the third coordination shell. So if you continue increasing, you will find the fourth neighbors, the fifth neighbor, etc. But at some point, if you increase the distance very far away from the central atom, at this point, you do not start, like there is absolutely no correlation between the position of this central atom and what happens at a very large distance. In a glass, there is no long range order like in a crystal. If you are a crystal, you know that there is some long range order. Why? Because a crystal is periodic. It means that if you know that this atom here, you know exactly that even very far away, you know exactly where the other atoms are going to be. In that case, it means that there is some long range order. If you know where the central atom here, you know exactly where the others are going to be, even if you look very far away. In the glass, there is no long range order. There is no periodicity. It means that if you know the position of the central atom, it doesn't tell you anything about the position of the atoms very far away. It means that as you go very far away, your chance of finding some other atoms, there's not going to be any excess of atoms or any deficit of atoms. Those atoms becomes uncorrelated to each other. They are very far away. So there is your chance of finding some other atoms is just the chance that you get based on the fact that the atoms at this point becomes randomly distributed. Again, like the fact that you have this central atom here doesn't tell you anything about where the other atoms are. It means that if you look at very long distance, your chance of finding atoms at very long distance is just your probability to find some other atoms is just given by the probability of finding an atom randomly in this box. It means that if you look at very long distance, your local density of neighbors, there is no special reason that it should be higher than the average density. There is no specific reason that it should be lower than the average density. So in probability, you have a chance of finding some atoms that is very close to the average density of the atoms within the box. And so again, if you look at very long distance, then since the local density becomes equal to the average density, then it means that the pair distribution function will go to 1. At large distance, the pair distribution function will go to 1, which means that you have no information about what's happening very far away from the central atoms. There is no excess, no deficit. So this is typically what the pair distribution function of a glass looks like. You have initially an excess of atom at the first peak. Before that, you have a deficit of atoms. So you have a deficit at very low distance, then an excess that would be a peak. Then you have another deficit after that, then another excess, etc. So you have a series of coordination shell where you will have a peak, which means that you have certain distances where you have an excess, and in between them you have a deficit. And at long distance, the pair distribution function will converge to 1. So this is the typical features of the pair distribution function. The pair distribution function of a glass will be 0 at low distance. The pair distribution function then will have some peaks at intermediate distance, and then as the distance becomes very large, the pair distribution function will converge towards 1 because there is no long range order within the glass. So when the distance becomes infinite or the distance becomes very high, then the pair distribution function becomes 1. Note that the pair distribution function can never be negative, like because the density of atoms cannot be negative. You cannot find a negative number of atoms at a certain distance. So the pair distribution function is always larger or equal to 1. So this is why this pair distribution function is very useful, because if you know this plot. So if you know the knowledge of the distance as the pair distribution function as a function of the distance, then you know what are the typical distance between the atoms, what is the typical probability to find atoms at a certain distance from each other. So of course, if you knew exactly where the position of the atoms are, where each atom is, then you can calculate the pair distribution function, but it's usually the other way around. Usually you can never know where the atoms exactly are. There is no experimental techniques that can look at a glass and see exactly where all the atoms are. But typically you can experimentally determine what is the pair distribution function of a glass. You can get this by diffraction experiments, either X-ray diffraction or neutron diffraction, for example. By using those diffraction experiments, you can measure what is the pair distribution function of a glass, and based on this pair distribution function of a glass, then you can get some information about what are the distances between the atoms, what is the probability to find an atom at another distance from each other. So usually this is why this pair distribution function is very useful to know some information about the structure of a glass, because you can access this information experimentally and then use this information to get some information about the structure, the atomic structure of the glass.